Analysis of variance. So in this video we're gonna analyze the variance. So we are going to use one-way analysis of variance via one-way ANOVA technique. And this way we are going to test the claim that involved three or more means. Okay? Pay attention, I don't say three or more samples. Three or more means. You will understand in a minute, just have a little bit patience. And then we are going to get familiar with two-way analysis of variance. Okay, one-way ANOVA. So one-way analysis of variance. ANOVA analyze the variance. So this is hypothesis testing technique that is used to compare means from three or more populations. Okay? Comparing mean from three or more populations. Analysis of variance is usually abbreviated ANOVA as an analysis of variance. Okay, this is what we are going to test. Hypothesis is if we have k amount of population, okay, and we are assuming that our mean for all k amount of populations are equal. This is what a hypothesis, null hypothesis, is gonna say. Alternative one, we say at least one of them, since we are comparing k amount of population. So if at least one of the means is different from others, then we say that they are not equal, and rightfully so, right? So let's do analysis. In one way ANOVA test, we have to follow the rules, and that is each sample must be randomly selected from a normal, approximately normal population. From normal and approximately normal population. Sample must be independent of each other, not dependable, and each population must have same variance, must have same variance. Okay, so when we are doing one-way ANOVA, our test statistics is going to be variance between samples and variance within samples. Let's say we have these samples from each population, and variance between sample, how far they are from each other. Maybe one is here, right? So how far they are from each other and how they influence each other, affect each other. And variance between samples we call MSB. Okay, mean squared between, that's what it is. Here it is, mean square between. Yes, that's an error. Mean squared or variance, that's a spread, right? The variance within sample, how they are spread within, that's what we call mean square within, and that is MSW. So the test statistics is equal MSB between over MSW within. Okay, so we're taking ratio between these two. Oh, here it is. Here we have statistical test is equal mean squared between, mean squared within. If the condition for one-way analysis of variance are satisfied, then sampling distribution for test is approximated by F distribution. Here it is. And the degree of freedom for F test, we know that for numerator is K minus 1 degree of freedom. And degree freedom for denominator is going to be N minus K difference. So K is a number of samples and N is the sum of sample sizes. Okay, it's crucially important to understand. Now, one-way ANOVA is operating based on one variable, independent variable between the samples and within the samples. One variable only. Okay. So here we have steps how we're going to do one-way ANOVA. I'm going to explain here how to do it, but when we solve the word problems, we are going to use technology, StatCrunch, and use ANOVA technique. But here I want you to understand how that black box that we are going to use. I need you to understand how is it working. So you can read in word problems, but I'm going to do this, show you based on example. Because I strongly believe it's better 1 time to see than 10 times to listen. Here, rather saying. Okay, so performing one-way ANOVA test. So we need to find, let me clean this table. I'm going to clean. And I'll post in the comments, I will post the table. Or you can search on internet also. F test table. Okay? All right. So, degree of freedom for the numerator, sample size, right? And N minus K, N is the sum of sample sizes of all existing samples. All right. So here is ANOVA summary table we have. So remember I said we are going to explore variation between samples, right? Here it is, variation between samples and variation within sample. So sum of squared is between, this is an error, right? Sum of squared, it's error spread, how far they are from each other. And sum of squared within, okay? So here we have degree of freedom for numerator, degree of freedom of denominator, and mean squared here is equal between, is equal SSB divided by degree of freedom N. So meaning we take this, divide by this. And mean squared for within, this one, we take sum of squared within, divide by degree of freedom within. Just so you understand, sum squared, it's nothing else but variance, the spread, how far they are from each other. Okay, standard deviation shows error in the sample, shows how far elements are from the mean. But variance is showing the spread, how far elements are from each other. Okay, and the mean squared between, a ratio divided by mean squared within, is our F, let me use black color, is our F statistics. Okay? Moving on. So, performing a one-way ANOVA. A medical researcher wants to determine whether there is a difference in the mean length of time. It takes 3 types of pain Okay, it takes 3 types of pain relievers to provide relief from headache pain. Okay, several headache sufferers are randomly selected and given one of the free medications. All right, each headache sufferer records the time in minutes how much it takes medication to begin working. The results are shown on the next slide. Okay, alpha equal 1%. Can you conclude that mean times are different? Okay, it's want to figure out, find the answer that mean times are different, which means this is our claim, alternative hypothesis that means are different. Assuming that each population of relief times is normally distributed and the population variances are equal. We assume that variances are equal. That is going to be our null hypothesis, because we always assume they are equal unless hypothesis test proves us point us to otherwise decision. Okay, so here we have medication 1, medication 2, and medication 3. Okay, below we have sample average. Okay, we are adding elements, dividing by amount, right? And we have the variation within each sample. S1 squared is 6, S2 squared 8.5, and S3 squared is 7. Okay, so we have 3 samples. This is our sample size, 3 samples, which means it's gonna be how we get medication 1, medication 2, medication 3 of them. N is equal sum of samples. First one, we have 1, 2, 3, 4. We have totally 4. Here we have 3, 5. And here we have 4. So we do 4 plus 5 plus 4. Yes? Okay. So our null hypothesis is equal. We always take null hypothesis equal, right? Mu1 equal mu2 and equal mu3. On iPad it got shifted here. Mu3, I can write down, no problem. Where is it? Mu3. And alternative, it says at least one mean is different. And that is our claim. All right, alpha is 0.01, it's given. Now degree of freedom for numerator, we have 3 total, right? It was k is equal 3, just to remind you. It's going to be 3 minus 1 equal 2. And degree of freedom denominator, we take the sum, right? Degree of freedom denominator, it's going to be equal 13 minus 3. Okay, it's our uppercase N is equal 13, right? So minus 3, because we are 3, it's a minus 1 for each sample, so total will be minus 3, and it's equal 10. Okay, now let's see how we are going to do test statistics and how we are going to draw decision. So first of all, let me transfer here on this slide all this data that we are given so we can make sense out of these calculations. So for first sample, here we have it. So we are using first sample, second sample, and third sample. For the first sample, we have sample size is 4. Second one is, how much is it? And 2 is 4. No, 5. and third one is 4 again. Next, x1 bar is 14, x2 bar is 17, x3 bar is 16.5. And variance of samples, S1 squared, 6, S2 squared, 8.5, and S3 squared is 7. Okay, besides, we total have K is equal 3, right? Total 3 samples. And sum of all 3 samples together is 13. Yes? Okay, now let's start working. So our final solution, we need to start from this formula that F test statistics is equal MS between groups, reaction of the independent variable between groups divided by reaction between independent variables within group. Okay, it's a mean sum between and mean sum within. Oops, W. Okay, so we are going to calculate MSB here, which is equal sum squared between divided by degree of freedom of numerator, which is going to be K minus 1. K was 3. Total samples, the sizes, total amount of samples, and minus 1. Okay, so but we have N, right? Sample size. We have X1 bar, right? But we need X bar, meaning average of all 3 samples. And here it is, we calculate. So practically we add all the 3 sample values from all 3 of them from the data, add them up, and we divide by total amount of sample size, which is 13, and we get 15.19. So our X bar is 15.92. Next, variance between samples is equal sum of squared between samples divided by degree of freedom that belongs to numerator, and that is going to be degree of freedom for numerator, that is equal degree of freedom for numerator, it's going to be equal sample size minus 1. So we have samples, amount of samples, I'm sorry, which is equal 3 and minus 1. So N is given, and we have, hold on, let me clean this so I can go over one more time. So N is a sample size, which is going to be 4, right? Let me take this. Okay. This is this 4. Okay, let me change the color, it's not seen. There, which is this 4, right? And sample size, it's this 4. And then we have, let me see what else I can choose, this one. So we have X bar for the sample 1, first sample, here it is, X1 bar, and minus X bar, that's the average for all 3, which is 15.92. And here we are plugging all these numbers. And that is squared. Since K minus 1 is the same denominator for all 3, so we just keep it as a common denominator, and moving to next one, plus. Next is going to be second one, 5, this is n, and then 17 is going to be x2 minus n 15.9, and then plus n 3, which is going to be 4, and then times 16.5, that's x3, and minus total x bar. And they get the result 10.96. Okay, we have that. Next, we need to find mean of samples within the within samples, right? Okay, let's do that. So here it is, but this is looks like numbers are shifted. It's not clear what is where. I'm going to clean this. Oops. I messed up. I need to get white color. Okay, so we need to calculate mean within sample, which is equal sum of squared within W divided by W divided by degree of freedom for denominator, which is going to be n, total amount 13, minus 3, total amount of samples, it's going to be 10. Now, and I'm going to clean this calculation because it's messing, everything is messed up there, it won't be clear. Okay, so let's start working. This is going to be equal n, how much was our n? 4. 4 minus 1 times s, how much was our s1? That was 6, right? S1 squared 6, and then plus n2 was 5, right? 5 minus 1 times s2 squared, which is 8.5, plus n3 was 4 minus 1 times sample, s3 squared was 7, and dividing by 10. So it's going to be equal, I'm looking from here, it's going to be equal 7.3. And from here, F statistics is going to be equal mean between samples divided by mean within samples, and we get 1.5. Okay? So, let's do test statistics finally. We have null hypothesis. We are testing that we are going to believe that they are equal, M3. Alternative, which is going to be our claim, at least one mean is different. And degree of freedom denominator we know already, degree of freedom for numerator we know already, sample size -2, and our alpha 0.01. F we already calculated 1.5. Now on the in the sample in the assignment, in many cases we are not going to calculate F test statistics, because we will use ANOVA technique and collect information from the table output report of ANOVA One Way ANOVA. Okay, so what do we get for 0.01 alpha? Let's see. Alpha equals 0.01. Our degree of freedom for numerator, we are going to find here, which is 2, and degree of freedom for denominator, which is going to be 10, we find here, and intersection, it's going to give us 7.56. 7.56. Yes? Okay. So this is going to be 7.56. It's going to be our critical value. Here it is, 7.56. And here we have also 7.56. And our, 7 point, that's a critical value. I'm sorry, here we have 1.5, which is our test statistics. And then we compare F statistics to comparing to F critical, and we are getting less than, because 1.5 is falling in the healthy area, right here, falling in the healthy area. Therefore, we draw conclusion that we fail to reject null hypothesis, which means for our claim it's going to be reject alternative hypothesis. If we reject alternative hypothesis, which means we are saying, using verbiage not sufficient, and using verbiage support. So we can say with at the 1% significance level, there is not sufficient evidence to conclude that there is a difference in the mean length of time that it takes the free pain reliefs to provide relief from headache pain. Okay, moving to next question. Using T8384, okay, this is same question, but it's using, or maybe different question, free samples, using statistical calculator, 8384. So here we have result, One Way ANOVA. You have MS, okay, and what else? You have here degree of freedom. I didn't read, was shortly saying, since we are going to work, whoever is interested, you can read, but we are going to work in StatCrunch, so once you work on StatCrunch, it will be very easy to figure out in the calculator. And let's get familiar with TwoWay ANOVA. So what is interesting about TwoWay ANOVA? That when we are doing test in two-test ANOVA, TwoWay ANOVA, we are dealing with more than one independent variables practically, and we are going to explore how these variables together affect a dependent variable and how they work between each other. Okay, so we are going to test for an effect from an interaction between these samples, which means we are going to use column and row interaction. That's in the technology, which means set of independent variables and dependent variables. And then separate, we are going to look testing effect from each of independent variable on dependent one. All right. So TwoWay ANOVA, what do we have? Suppose a medical researcher wants to test the effect of gender and type of medication. Where is our gender? Our gender is here, male, female, and medical type, it's horizontal, so we are using end column and row, and type of medication. On the mean length of time it takes pain reliever to provide relief. All right. So main effect we are going to explore, it's effect of one independent variable on the dependent variable. I already said. Interaction effect, it's when both independent variables on the dependent variable. I talked about it a minute ago. Okay, this is about TwoWay ANOVA hypothesis. So hypothesis for main effect. To remind you, main effect is each independent variable on dependent. So what's gonna be null and alternative? That gender has no effect on the mean length. So gender is gonna be gender is gonna be our the independent variable, right? And mean length of time is going to be our dependent. So has no effect, and alternative will be has effect. So the second version, their interaction between variables, independent variables and dependent ones. So type of medication has no effect on the mean length of time it takes a pain reliever to provide relief. So this is type of medication. In the previous, this hypothesis higher here, we used gender. Now we are going, that was in column, right? Gender, male and female. So those were columns. But now we are going to look in a row, which is going to be medication, how it's affecting. So type of medication has no effect, and this is where we say that they are interacting between each other. So type of medication has no effect on the mean length of time it takes a pain relief to provide relief. And alternative type of medication has an effect, okay, on interaction. So just to remind you, so main effect is the effect of independent variable on dependent. Interaction when both. So see, our interaction would be in a case of medication, right? We have several medication here. Going, medication going horizontally, right? Correct? That's what it is, interaction effect. All right, so this is our null hypothesis for the main side and interactive side. So two-way ANOVA hypothesis for interaction effect. Now it's there is no interaction. Did we look? Yeah. Not now interaction for effect. For null hypothesis, meaning there is no interaction effect between gender and type of medication. Now we are looking in between. This for medication, different medication, medication 1, 2, and let's say 3. Here we have male, here we have female. So we look separate male and female. We look at that we did hypothesis testing claim based on medication. Now we're looking in between male and medical type, female or medical 2 types, let's say. So there is no interaction effect between gender and type of medication on the mean length of time it takes pain reliever to provide relief. An alternative, there is an interaction. There is. Here there is no. Okay? So we are going to perform two-way ANOVA test, calculate F statistics for each hypothesis. If it's possible to reject none, one, or two, or all of null hypotheses. The statistics provided involved with two-way ANOVA test is beyond the scope of this course. So, but we can use our stat crunch, and we successfully will do our two-way ANOVA. Okay. And that's all. We used one-way ANOVA, and we got familiar with two ways analysis of variance. So now I will start recording the assignment, practicing problems. Okie dokie.